In our discussions of semiconductor device fundamentals, we established the fact that silicon will, because of the proximity of all the silicon atoms, will result in this thing called a valence band and a conduction band, where the valence band in the crystal under thermodynamic equilibrium will be filled with a lot of electrons, and the conduction band is a higher electron energy level, which allows the electrons to move, sort of wander throughout the crystal structure of the silicon, but this band has relatively few electrons in it. Okay, and the separation, the energy that separates the difference between those two gaps is called the band gap. Now, it's typical to represent a semiconductor system using the band gap and a simplified schematic for this band gap diagram. So typically we just represent the valence band maximum energy and the conduction band minimum energy as two lines. Okay, and the separation distance in between the two of them is called the band gap. Now, there's another thing that we need to be aware of conceptually, and this is called the Fermi energy level. Again, all of this is fairly complicated and derived from semiconductor fundamentals, which is not the intent of this course. But nonetheless, to be able to sort of talk about these devices, we need to know some of the basics here. So the Fermi energy level is this imaginary energy level. Remember that no electron can have an energy level, have an energy that resides within these areas, within this band gap region. So no electron can have an energy that corresponds to an energy within this region right here. But nonetheless, we established this thing that's called a Fermi level. And the Fermi level in a semiconductor like silicon lies right in the middle of the band gap. Okay, well, not all the time. We're going to talk about when deviations from that occur. But right now, if it's just a lattice comprised of all silicon atoms, it's going to have a band gap, and the Fermi energy level is going to reside right in the middle of that band gap. So the Fermi level is defined as being the energy level where there's a 50% probability of the states being filled. So what that means is there's a 50% likelihood that states below this will be filled, and there's a 50% likelihood that states above this will be unfilled with electrons. Okay, so in this case, this Fermi energy level describes the fact that under most conditions, the majority of electrons are going to be residing in the valence band, closely associated with their with the silicon nucleus, and there's going to be a low probability that we're going to have any electrons in this conduction band region, or being able to sort of wander throughout the crystal. So this semiconductor that's comprised of all silicon atoms actually is not very interesting to us because all it's going to do if we apply a potential across it is it's going to act like a resistor because we're going to supply a little bit of electrical energy to it, and some of the electrons are going to increase their potential energy, and if we provide sufficient potential energy, they will be able to make it to the conduction band and wander through the material, causing a current, a net current flow. But it's all that is going to happen is it's going to dissipate energy and it's going to act like a resistor. So that's not a very interesting phenomenon. But how modern semiconductor devices work is through this process of doping. So instead of taking a material that's comprised fully of silicon, which we call an intrinsic semiconductor, what we do is we take that intrinsic material and we add some impurities into it. So essentially we dope the material. That's what this process is called. Okay, so we create two different types of semiconductor materials. One is called an N-type and one is called a P-type. So to create the N-type material, what we're going to do is we're going to, as we're building our silicon lattice, what we're going to do is we're going to introduce impurities of phosphorus into this lattice. So we're going to, every once in a while, substitute a silicon atom for a phosphorus atom. So this is done using a chemical process. And if we look at our periodic table right here, we see that phosphorus is located one to the right of silicon. So this one has 5 valence electrons to it. Now remember that silicon has 4, and that's why it covalently bonds into this nice crystalline structure. But every once in a while we're going to toss in a phosphorus atom in here that has 5 valence electrons. And what's going to end up happening when we do that is that we get this nice lattice structure, with the exception of around this phosphorus atom we have this electron that doesn't really have a nice place to live. Remember that the valence shells, we want to fill all the valence shells, and each silicon atom is going to be happy when it has a total of 8 electrons surrounding it or shared with other atoms. So in this case, we're going to have an extra electron in here, and this extra electron is going to have more energy associated with it. So it's going to be associated with this phosphorus atom, and it's going to be orbiting around this phosphorus atom, but it has a higher energy level. And that energy level is going to reside somewhere closer to the conduction band than it is to the valence band of silicon. Alright, so what we're going to do is we're going to introduce a couple of atoms interspersed throughout this silicon lattice, and they're going to have some extra electrons that are going to be have an energy that resides within this band gap, and it's only going to take a little extra energy to pop one of those electrons up into the conduction band of this entire crystal. Now remember, this is not violating the principles that we talked about before, because this is actually a different material now that we have a little bit of phosphorus doping in here. So the phosphorus atoms are going to contribute the possibility for having the conduction band have a little bit more population of electrons or charge carriers that can move throughout the material inside of it. So in this case, the Fermi energy level, because we've added these extra electrons here, the Fermi energy level is going to shift upwards, because now there's a greater likelihood that we're going to have some electrons populating the conduction band. So our Fermi energy level is going to shift up in this a bit. Now, it's important to note that what we've done to this material now is we've taken silicon atoms and we've taken this phosphorus atom, and we've added this phosphorus atom into this lattice. Now the doping is on the order of 1/10% to 5, 10, 15%, depending upon what's trying to be meant to be accomplished by doing that. And the more dopants we add, the greater this Fermi level energy level shifts upwards, up to a point wherein we've created a completely new crystal that has a different band structure associated with it. But in this case, we're adding low levels of phosphorus, and we're increasing the probability that we're going to have some electrons that are excited and in the conduction band that can move throughout the crystal. Now, it's also important to note that silicon and phosphorus both have different atomic numbers, and what I've done here is I've added this thing, this extra electron. So what is the net charge going to be when we dope silicon with phosphorus? Well, you might think that since we've added an electron here, we're going to end up having a net negative charge in this piece of silicon material that we've added phosphorus to. But that is not the case, because remember, the phosphorus atom has a balance of electrons and protons, as well as silicon always has a balance of electrons and protons. So phosphorus has one additional proton, but we also add that additional electron in here. So it still maintains a net neutral electrical charge associated with it. The only thing that this does is add this extra higher energy electron that we can easily add a little bit of energy to and cause it to move throughout the crystal. Now, a p-type material, on the other hand, we're going to do the opposite with. We're going to dope silicon with boron. All right, and if we look at boron, boron resides on the periodic chart one row up and one column to the left of silicon. So what this means is that it has one fewer valence electrons than silicon does. So now if we come back here and we look at what will happen with boron, if we add boron impurities into the lattice, what we're going to end up doing is there's going to be a region, around that boron atom, there's going to be an absence of an electron. Again, the net charge on this material is neutral because boron has one fewer protons and one fewer electrons. But now what we've done is we've created this region where this boron atom wants to try to grab electrons, if you will, from its neighboring atoms, from the neighboring silicon atoms. And we call this, the absence of an electron, we call it a hole. All right, so this is conceptually what's going on here is we pretend that this absence of an electron acts just like an electron with an opposite charge. All right, and we have that hole, and holes, since they're anti-electrons, they want to decrease their energy. So adding this boron, what's going to happen is it's going to add the possibility that these holes are going to decrease their energy, or we're going to promote an electron into these states, into these boron states right here. And when that happens, these holes can move throughout the material. So we have charge carriers, a positive charge carrier, which acts like a hole, and these holes can drift throughout the material and cause a current flow as well. In this case, the Fermi energy level for a p-type material, because we have a greater probability of there being electrons in the valence band, or below the middle of the band gap, we have a greater probability of electrons residing here and giving energy to these intermediate states right here, as opposed to the valence band, or excuse me, the conduction band. The Fermi energy level lies lower in the p-type materials. So the interesting things start to happen when we put these two materials together, and that forms the basis of a diode, which we'll discuss in the next video.